So, good morning. I will be taking you on the topic radioactivity. And my name, as always, is Mr. Oza David. Now, before I start with the topic, I would want to draw your minds back to one of the theory proposed by Dalton. I could recall that Dalton said matter can neither be created or destroyed. That's one of the postulates of the Dalton's theory. But if you recall back then, we were taught that radioactivity, the phenomenon of radioactivity, is one of the theories eventually that disproved that theory, that matter can be created and destroyed. Hence, I would love to take you through on the topic of radioactivity. What is radioactivity? Well, radioactivity can simply be defined as the spontaneous disintegration or breakdown of an element which was ordinarily unstable to make it relatively stable or totally stable. And during the process, emission is emitted. Now, to help us visualize this, I will be making use of some pictures and illustrations as you'd see on the screen. Now, if you look through the screen now, you see uranium-238, which we would call an unstable element or nucleus. Now, if you look clearly at the diagram, you see that there are some particles in it that actually makes it unstable. After emitting those particles, uranium became thorium-234, which is now relatively more stable. So that's just what the phenomenon of radioactivity is all about. We have an element which in the course of this topic we'll be calling a nucleus that was unstable. It will adjust itself, it will disintegrate, it will break down, and at the end of it, it becomes stable. Now, during this process of radioactivity, as we have seen, the uranium, which was the starting element, is no longer found in the product. It has been destroyed. And thorium, which was not part of the reactant, is now found in the product. It has been created. And of course, just like I mentioned, this is one of the ideas that disproved Dalton's theory. Now, although this theory of radioactivity or this phenomenon, in the process, a number of particles and radiations are emitted, we'll just be considering the three main particles or emissions, so to speak, or products of the process. Now, if you check the screen again, you will observe that we have the alpha particles, the beta particles, and the gamma, which of course is not a particle, but an electromagnetic radiation. Now, I've made a table to compare each of these products. You can see the alpha particle, as you can see, it is helium. Especially when we work with nuclear equations, you'll notice we write helium with a mass of 4 and atomic number of 2. Our beta particles are actually electrons with a mass of 0. Of course, we could think about the fact that electrons are 1 all over 1840 of your proton. If you divide that, you get 0.00 as the case may be, so approximately 0. And of course, gamma, which is an electromagnetic wave. Now you notice that the alpha is positively charged, the electrons beta they are negatively charged, and your gamma actually has no charge. Of course, we've also compared their velocities. But now we want to pay close attention to how they are affected by an electromagnetic field. Now you notice that depending on their charge, they are affected differently by an electromagnetic field. So we'll observe the screen again and see how we'll show how they are affected differently in the electromagnetic field. You notice that the alpha particles being positively charged are attracted to the negative end. The beta particles being negatively charged are attracted to the positive end. And the gamma particles having no charge will simply pass without deflection. And this agrees with the law of electromagnetic electrostatics that unlike charges should attract. So that is also one of the things we observe in our table. Another thing you notice in the table is that their penetrating powers are different. Again, to illustrate this, three materials are usually used. We have our thin sheet of paper, we have our aluminum foil, and also we have the lead block. As you observe again in the screen, you notice that alpha particle can be stopped by a thin sheet of paper. The beta particle will pass through your thin sheet of paper, but when it comes across aluminum foil, it is stopped. Your gamma, on the other hand, will pass through the paper, pass through the aluminum, but when it gets across the lead, it's stopped. Hence, that is why if you check the table, we said your alpha particle has the lowest penetration, your beta particle has a moderate penetration, while the gamma radiation has the highest penetration. At this point, we want to focus now on the various types of radioactivity. Basically, there are two types of radioactivity. We have the natural and the artificial. Of course, we call it natural or artificial based on whether it is induced by man or it occurs naturally. We call it natural when it occurs because the nucleus was naturally unstable. Hence, it has to disintegrate. It has to break down to become stable. Of course, we call it artificial when it is induced by man. And as you can see from that diagram, it is also divided into two. We call it nuclear fission and nuclear fusion, depending on how the process is carried out. So let's talk a little about natural radioactivity. Now, how do we observe natural radioactivity? Well, the example we gave at the beginning is a typical example of natural radioactivity. If you focus again at the screen, you would see that in natural radioactivity, the nucleus in question was naturally unstable. Uranium was naturally unstable. Nothing was done to it, but it disintegrated to give thorium and emitting another particle as a byproduct. Thorium was originally unstable. Nothing was done to it, and it formed another element, polonium. Radium was also unstable. Nothing was done to it. It gave rise to another element. So this is what we mean by natural radioactivity. That is why it is spontaneous, because it occurs on its own. But what about the artificial kind of radioactivity? Well, just like we have said, anything artificial is induced by man. The element was originally stable, but in this case, it's now being bombarded with radioactive particle, causing it to become unstable and disintegrating in the process. If you see the equation we have on the screen, aluminium was stable, but because it was bombarded with helium, it becomes unstable and disintegrated. Boron was naturally stable, but because it was bombarded with alpha particle again, it becomes unstable and it disintegrated. So some particles used for such bombardment are the proton, the alpha particle as we have seen, and the neutron particles. Now, you noticed earlier on that I mentioned that there are two types of natural artificial radioactivity. We have the nuclear fusion and the nuclear fission. So let's focus a little now on the first one, the nuclear fusion. Now, as we know, fusion has to do with combination. So we see your deuterium, which is an isotope of hydrogen with a mass of 2. We see your tritium, an isotope of hydrogen with a mass of 3, being combined to give a product, helium, which now has a mass of 4. So that's why we define nuclear fusion as combination of two lighter nuclei, your deuterium and your tritium, both lighter than helium, and during the process, energy is emitted. This is an example of nuclear fusion. Now, the second one we'll talk about is the nuclear fission. Now, fission has to do with splitting a heavy nucleus now being split into lighter nuclei. So if you focus again on the screen, you will see how we illustrate this with uranium. Now, if you look at the screen, you see that uranium 235, it's a heavy nucleus. Now, it's now being bombarded with neutron particles, and during the process, two new nuclei are formed. Now, if you compare the masses of uranium, which is the only element in your reactant site, now eventually we have given rise to two products. So it's the uranium now splitting after being bombarded into barium and krypton. So this kind of process is what we call fission. So what's the summary? In nuclear fusion, we have two lighter nuclei or two elements on the reactant side combined together to give one heavy product, one heavy element on the product side, fusion or combination. What about fission? You have one element on the reactant side with a particle which is not an element, but after being bombarded, you split to get two products on your product side. So that is fission. Now, having talked about this, we can also bear in mind that there are some important terms associated with radioactivity. For example, when only alpha particle is emitted, we call such a decay alpha decay. When only beta particle is emitted, we call such a decay beta decay. And of course, when only gamma radiation is emitted, we call it gamma decay. For alpha decay, the mass reduces by 4 because the alpha particle has a mass of 4 and the atomic number reduces by 2. For beta decay, the mass reduces by it remains unchanged, while the atomic number increases by 1. And for gamma, the mass and the atomic number remains unchanged. Now, at this point, we want to talk about a very important concept in radioactivity, which is called the half-life. Now, half-life is defined as the time it takes for a radioactive particle to become reduced to half of its initial value. What do we mean? For example, the radioactive particle has 10,000 particles. The time it will take for it to become 5,000, or the time it will take for 5,000 particles to become 2,500. So that is what we call the half-life. Now, this is the general a curve for half-life. And of course, this will take us to some calculations associated with radioactivity. If you look closely at the screen, I have extracted 4 different formulas. These are the key formulas you would use when it comes to questions involving radioactivity. So if you check the screen, you notice that the first one is the formula for the half-life. The second one is the formula for the number of half-lives. The third one helps you to relate the particles at the beginning, particles at the end with your decay constant and time. And of course, the fourth one is what we call the Einstein's equation, which converts energy and mass. Now, let's define each of these parameters. What are these parameters? What do they stand for? Especially if you are to apply them in a formula. If you look closely at this, at the screen again, you notice that each time you see T half, that is our half-life. Each time you see small letter t, that is our time of decay. Small letter n, number of half-lives. N naught, particles at the beginning of the decay, which in most past questions they call initial activity. Your n, particles at the end of the decay, which they call final activity. Lambda is your decay constant, E is your energy liberated, change in m is your reduced mass, and of course c is the speed of light, which has a value of 3 times 10 raised to power 8 meter per second. So at this point, I want us to solve some examples. I have a jam question on the screen now. Let's look closely and see how we would solve this question making use of the formula. Specifically, observe how I determine which formula I'm going to use. Where am I going to use it? How am I going to use it? So the question says, an isotope has an initial activity of 120 BQ. So what's that? 120 BQ initial activity, that is your N naught. 6 days later, what's the 6 days? Total time of decay, that's your small letter t. And of course, the activity at the end, it calls it 15 BQ. What's that? That's your capital letter N. Now we are told to find the life. So the first thing I tell my students is that whenever you are solving a question in mathematics, whenever you are solving a question in physics, whenever you are solving a question in chemistry, the first thing to do is always to bring out your parameters. Now, based on your parameters, you cannot decide the choice of formulas to use. Now, based on the question we've just read, I have brought out my parameters, my N naught, my N, my small letter t, and my half-life. Now I'm told to look for half-life, which is my T half. Of course, to get half-life, I'll need my decay constant, which of course I do not have. That means I will need to use the other parameters in another formula to get my decay constant, which I cannot apply in this formula. So which formula is that? I guess your mind will go back to formula number 3. So if you check again, you notice that I will now go back to formula number 3. Formula number 3, which we have said earlier, connects your decay constant, your time of decay, and the number at the beginning and end. Now, starting each of the values in this formula, as you can see on the screen, it is now possible for me to get my value for decay constant. And of course, if I can get the value for decay constant, it is not possible for me to insert it into the equation and get my half-life. So it's as easy as that, as we have seen on the board. So the final steps now leads me to getting my decay constant, and of course, it leads me to getting my life. So if you look at the screen again, you see now that substituting it, I've gotten my decay constant. And eventually, if I substitute my decay constant, it leads me to getting my half-life. So the final step is showing again on the screen, and you see how I eventually use this, and it's possible for me now to get my half-life. So how easy was it for you to get the half-life? Well, if you want to watch through the summary of the whole thing, now the summary of everything we've just done to get the half-life now shows on your screen. Remember the 4 steps? Step number 1, I say, bring out your parameters. Step number 2, looking for half-life. So I bring out the formula for half-life, but I don't know lambda. So I have to think about how do I use the other parameters to get lambda? And that is where I built in another formula. Solving for the decay constant, I substitute eventually, and I get my half-life. A second question I want us to treat now is the case of radioactive equations or nuclear reactions. This is another common question you see in past questions, precisely. Now I have a JAM question again, because most of us now are preparing for JAM. I have a JAM question on the screen. It says you have sodium combined with a proton, an element X is formed, and alpha particle is released. That's an alpha decay. Find P and Q. Of course, we know P is the mass of the element and Q is the atomic number. Now, how do you go about it? Well, if you have such an equation, just like I said, you have to write each element showing both the mass number and the atomic number. So we can recall that in radioactivity, there are some basic things we must always have at the back of our mind. For example, we want to have at the back of our mind that alpha particle is helium, mass of 4, atomic number of 2, beta, mass of 0, atomic number of -1, that's electron. Gamma, because it has no mass, no charge, we give it 0, 0, your neutron and your proton. So I guess you understand now that I will quickly substitute my alpha particle for helium with a mass and atomic number, and I'll substitute my hydrogen for proton with the mass and atomic number. If you check again at the equation, you notice that that was this next step we have done. And of course, with that, you can now know what else to do in each cases. So the equation looking like this now, it is now possible for me to solve. Now, for such equations, the general rule is that the total masses on the left-hand side, that's your reactant side, should be equal to the total masses on the right-hand side, that's your product side. And the same thing, the total masses on the atomic numbers on the reactant side must be equal to the total atomic numbers on the right-hand side. That's your product side. So if you check it, 23 plus 1, comparing the mass is 24, and that should be equal to P plus 4, making P the subject of the formula, meaning the mass is 20. Comparing the atomic numbers, 11 plus 1 should be equal to Q plus 2, making Q the subject of formula, we got 10. Some questions will ask you to predict the element, and I guess you know the element is your neon. So, at the end of these 2 questions, I also have an assignment for you. I want you to look closely at this assignment. It looks exactly like the questions we have just solved. The first one is a WAEC question. If you look at it, it says, it says an excavation. In an excavation site, a bone was brought out. In initial activity is 12 PQ. I guess we know what that is. After a period of time T, the activity is now that's our final activity. You are given your half-life and you are told to find the age of the bone, that is letter T. Now, I think that's going to be very easy for us now based on the first example we have solved. Now, what about the second assignment? Well, if you look again at the screen, this time I have chosen another one just like the second one we did on nuclear equation. So if you check the second one now, you notice that, okay, so the second one is that of a nuclear equation, you notice that we are told to find element x. I'm giving you the hints. What you have to do is, remember, we balance the mass numbers and we balance the atomic number. So give the mass number of x an unknown letter A and the atomic number an unknown letter B, and all you have to do is balance them, and you can predict the elements that x stands for. So that's all about radioactivity. But in summary, remember, we said it is one of the phenomenon in physics and in chemistry that actually disprove Dalton's theory that atoms cannot be created or destroyed, because we've seen that an element is actually destroyed on the reactant side and the new nucleus form is being created. We've seen that there are two types. When it is induced by man due bombardment, it is artificial. When it occurs because the element was originally unstable and wants to become relatively stable, it is natural. We have seen that during the process of radioactivity, basic particles, radiations are emitted, but the three main ones we've talked about are the alpha particles, the beta particles, and the gamma radiation. We've seen that among the artificial, it is either nuclear fission and or nuclear fusion. When two lighter nucleus have to combine to give one heavy nucleus, just one product on the product side, that is nuclear fusion. When one element is bombarded with a particle which is not an element, and eventually you have two new nucleus form, it is called nuclear fission. And of course, we've seen the formulas for half-life and how you can apply formulas in solving radioactive problems. So that's our class for today. I believe you've learned something. See you another time.